So let's start today. So we're going to change gears a little bit, and we're going to change our perspective. So I know you guys are all sort of deep into MPI right now, but we want to look a little bit beyond, and we're going to switch to MapReduce, which is sort of become the de facto framework for doing big data computations. In many ways, it's not ideal, but sometimes you have to go along with what is most popular. Keep in mind that I'm saying MapReduce and not Hadoop, although that sort of ends up being the most popular implementation for this. We're going to look at MapReduce, the basics. We're not going to get too deep into Hadoop, at least not for this lecture. What I want you to understand is, what are the motivations for developing something like this? Keep in mind that MPI is much older, has been around, and is much more stable even. So what are the motivations for developing or coming up with a system which in many ways is going to look inferior? Okay? So you need to understand the scope within which MapReduce makes sense. We are also, let's actually go with the start. So last time we did MPI-IO and we did randomized algorithms, both parallel, K-select, and graph coloring as examples. And then we had assignment 2. Any questions regarding this, or can we move on? Any of these topics, it's clear? Okay, good. So as I mentioned, we're going to talk about MapReduce. We're going to go over, I'm going to give you a quick overview of what the general idea is and in which cases it makes sense. What are the inherent assumptions made about the kind of problems that you are expected to solve using MapReduce. We're going to go back to our favorite example. We're going to look at matrix multiplication coming up again now. So we looked at how we would do matrix multiplication in an MPI format setting. And here now we're going to look at how does that map onto MapReduce. I want to give you a little bit of an early, I know you're still with assignment 1. The next assignment is going to require you guys to implement PageRank, which, if you remember initially, that's what made Google famous. So we're going to look at that, and you will see that matrix multiplication ends up being a somewhat essential part for that. So this lecture, leading up to the next lecture, we will focus mostly on PageRank. What are the issues? You should understand how we're going to do it, and it's not immediately straightforward. We're also going to look at complexity theories. We looked at analyzing parallel algorithms, specifically in a message passing environment. A lot of that carries over. However, because of the way or the kind of problems and the kind of architectures where MapReduce is typically run, you have to prioritize different aspects. It's not as powerful as MPI, so you don't have the same level of flexibility, which means that the way you analyze an algorithm, or the way you would say that I need to do something like matrix multiplication, how do I go about doing this in MapReduce? You can come up with 2 or 3 different techniques, even before you start writing any code. You need to understand how we can analyze these approaches, figure out whether those are effective enough and if they are efficient for MapReduce. So we're going to look at how we analyze the complexity, hopefully predicting both the runtime as well as the scalability of these kind of algorithms. Now, MapReduce started off primarily as a data processing framework. So it's not fair for us to look at it as a parallel programming framework. The inputs, the intermediate steps, the way you process all happens from the file system. So at the fundamental level, you're talking about manipulating data which sits in files in a distributed file system. And implementations usually are accompanied by their own distributed file systems. So one of the fundamental reasons is that if you have a distributed file system, the files are not going to be contiguous, they're going to be divided across files, and we're going to call them as chunk. You have two kinds of tasks which are going to manipulate this data for you: the map tasks and reduce tasks. The map task, as it listed out here, it processes the input data and generates local results, which are then aggregated and merged by the reduce task. So fundamentally, you're looking at two steps, which should already tell you where the first limitation comes out here, that you're only talking of something which can be parallelized very effectively into these two tasks. One which is very embarrassingly parallel and one aggregation step. Anything which doesn't directly fit into this is either going to be very inefficient to implement or is going to require multiple stages. Because the motivation was for data processing, the input and the outputs for these are much more standardized than, say, MPI, which is open-ended. So whether it is for the map tasks or for the reduce tasks, you generally can make an assumption that everything is going to be in terms of key value pairs. You can just think of these as some key or an index and the associated data with us. The keys are what we are going to use to pair these together. This is somewhat, not exactly, because this is now tied up with the data as opposed to the processors. In concept, you're going to use this similar to how you use the ranks for the processes. Make sure you understand the distinction that here we're looking at assigning these or enforcing the parallelism at a data level as opposed to a process level. It's a subtle difference because there we go to data parallelism via the process parallelism, whereas here inherently we are starting off with the notion of the data itself being parallel. It's not always needed, but it's nice because you can think of a complex workflow being a set of MapReduce tasks stacked together, pipelined one after the other. So it sort of helps to think it that. Let's look at some of the motivations. The central reasons for some of the design quirks that you will observe with MapReduce come from the fact that they prioritize fault tolerance over performance. When we consider fault tolerance, you have to consider that these are for large-scale data processing. So you need your system to be robust enough to a single node failing, which means a single machine in part of your network goes down, or it's possible that you lose, let's say, network connectivity to an entire rack. So a whole set of machines actually goes offline. The files or the data that you're processing is going to be very, very large. So that is the other consideration. And this is a very, very important factor that is going to limit what kind of applications you're going to consider for MapReduce. Is that the inherent assumption is that files are rarely updated. So you have a very large data file, some data, where you're going to be reading it and you're going to be performing calculations, but you're only going to update or modify the data very, very rarely. And sort of that is a good estimation of the cases where MapReduce ends up being a good framework. So if you have a large data set, but if you're manipulating it all the time and you're modifying it all the time, MapReduce from the start is not going to be a very good framework for this. Whereas if you're reading and you're extracting some information and adding some information, typically in an append style, rather than by modifying existing data, then MapReduce is going to be very efficient for this. And this just comes from sort of the background of how it started off with. The other assumption that is made is that your entire task, the task that you wish to achieve, is dominated by communication costs and I/O. We expect that the files are sitting on disk in a distributed fashion, and that we are going to be communicating these across our nodes. So those are what dominate, whereas the actual computation that you're doing, the actual calculations, are so cheap, they're typically linear in the file size, which means that the cost of reading this file, and you will probably notice this when you look at sort, for example. in most cases, the cost or the time it takes for you to read the data and write it back to disk is going to be greater than the time it takes for you to sort it. So those are the kind of operations that map reduces. And sort is probably still requires a little bit more work than some of the other calculations that you're doing. The other assumption, and this is sort of related to the fact of files rarely being updated, is that your problems are dominated by input size. So we're saying that the input size is huge, the input file is huge. The size of my output, right? And this comes from the fact that we're doing some mapping followed by a reduction, is that the output size is significantly smaller than the input. So as we, later in the lecture, when we look at complexity theory for MapReduce, you will notice that we are mostly modeling it based on the input size, which we use as an indicator of the amount of communication or the I/O that we use. So all our modeling now is going to be done mostly on the input size, the cost of reading the file or cost of communicating this input to all our processes. In NPI, by contrast, we were mostly interested in what is the complexity of performing the calculations of the actual algorithm. So when we model this out here, we are mostly interested in communication and I/O. Okay, so that's the single most important fact. You will see, of course, especially when we do the matrix multiplication, that it's going to end up with similar algorithms, so to say. The same kind of ideas are going to be reflected out here, although we're going to take a different path. And it's important for you to sort of understand and appreciate both approaches, irrespective of which system you're using. So the stereotypical example that you would think of is basically of doing a word count in a bunch of web pages or a bunch of documents. And you can think of how you would parallelize something like this. These are, even before you get to MapReduce, if you think of doing a word count on a bunch of files, it's inherently easy to parallelize. And those are the kind of problems that you will typically see are being applied to MapReduce. We can parallelize, and here we assume that we are parallelizing at the scale or the granularity of a single file or a single web page. So the input could be, again, like I said, it's time to start thinking in terms of key value pairs. So you can think of the key as being the page URL and the value being the page content. And the output eventually is going to be a bunch of key value pairs where the key is the word and the value is the total count on all of these, across all of these files. For this particular file, and the reduce task is going to take this across all of these files and it's going to merge them together to give a single output where it's the word and it's the global word count. Okay? So what are the dependencies in MapReduce? So the fundamental thing, again, I'm repeating myself, is that all the map tasks are independent of each other. And when you design map tasks, that's what you're trying to do. In cases where your underlying problem does not allow you to do this, these are going to be difficult problems to parallelize using MapReduce. So they're all independent of each other and can run in parallel. This is what we would typically call as embarrassingly parallel tasks. The map task must finish before the reduce task that process it can actually go ahead and process the data, and this is just the dependency that you define. In many of these cases, certainly true for a lot of the examples we're going to consider today, the reduce tasks are commutative, which means that the order in which you merge them together does not matter. In some cases, this might not be true, and we'll take a look at some of those examples later. What this means is that if you think of this as graph, again, think from a data perspective of how data moves across your different tasks, whether they are map tasks or reduce tasks. We typically end up with an acyclic graph model, and this is what we're going to use eventually to model the complexity for MapReduce. Most of you probably know this. There's a bunch of implementations. The original MapReduce implementation was from Google and described in their very famous paper from 2004. This implementation is not publicly available and was written in C++ for efficiency reasons. The most common implementation came out of Yahoo and later by Apache, which is Hadoop. It's an open source implementation, and along with its HDFS, the distributed file system that goes with it, is very popular, and there are variations out it, mostly driven through a Java interface, although there are mappings available for a bunch of other languages. There is a open source C++ version called Phoenix++ that you can play around with on your laptop if you want. It basically is a shared memory implementation of MapReduce. Do you think it makes sense to have a shared memory implementation for MapReduce? What do you mean? Sorry?
So people who are really used to writing code in MapReduce can easily import it.
But what do you think about the performance? Is this better than using, say, OpenMP or some threading framework? Yes.
Sounds contradicting to what you were saying. The design principle was basically your file system, and now using shared memory.
Exactly.
The communication cost was high, whereas this is.
Yes, so this is probably beyond an educational tool, or if you just want to experiment with it. It doesn't make sense. It's surprisingly somewhat popular, and the paper got a lot of citations and I think some awards as well, but fundamentally it doesn't make sense, at least if you're targeting the shared memory system and you're targeting a multi-threaded framework. Like I said, for an educational sense, it makes sense. If you want to say that I don't want to have a full-fledged system out there, I'm interested in understanding the programming model, then it makes sense. So you can try, yes?
Is it like, does it have like better performance than Hadoop?
No, it won't. Well, it's in some sense it would, because it's basically relying, it's a single node machine, so it doesn't have the same kind of overheads as Hadoop would have, spanning across a cluster, as well as dealing with things which are on a distributed file system.
Yeah. So for a company which needs like certain kind of applications, they probably have developer to Hadoop.
So if you are a company and you had your own dedicated hardware, one, you're going to probably be still better off with a standard shared memory implementation, something say using OpenMP or thread building blocks or any such, pthreads, any threading framework, or even using MPI for that matter. Actually, MPI would probably win in most of these cases. So it's a trade-off, but it's good for you to know at least that. I want to also, because we are at this thing, I want to make a distinction at this point, especially when you consider MapReduce to MPI, right? So I told you that from an algorithmic perspective, or the flexibility, MapReduce is vastly inferior to something like MPI. But let's think of it, there are two separate aspects out here. The actual implementation wise, so let's separate out two separate tasks. One is you as a developer implementing some algorithms on top of these frameworks. So Hadoop exists, MPI exists, some implementation, and you want to go ahead and implement matrix multiplication using both of these frameworks. That's one task, and there is a difficulty level associated with this. The other part is you being a core developer for one of these frameworks and you having to implement, say, Hadoop from scratch or having to implement MPI from scratch, okay? And you need to sort of understand where they are. MPI in its basic form would be much easier to implement than Hadoop would be, as in if you are a developer developing these frameworks. Whereas writing a piece of code that runs on these systems, ignoring performance, Hadoop is going to end up being much easier, mainly because you don't have to think much. There is a map task and there is a reduce task. You're not doing too many complicated moves. There's less, let's say, moving parts for you to deal with. And that sort of boils down to where the focus of these two approaches is. MapReduce ends up being something which is easier to implement, mainly because algorithmically, you don't have to think as much. You are sort of working with your hands tied behind, which means that there are limited approaches or limited techniques that you can use to expose the parallelism. which makes it somewhat easier. But behind the scenes, your basic MapReduce implementation, say Hadoop or the Google implementation, are doing a lot of things on the file system level in terms of gathering all your key value pairs, figuring out where it gets scheduled. Some of these actions are actually done by you directly if you were programming in MPI. And that's where the trade-off is. It is inefficient because Hadoop or MapReduce in general ends up being inefficient because the system does a lot of work for you, right? So we are looking purely from the perspective of implementing algorithms here. If it were to the fact where you have to implement something like this, Hadoop is way more complicated because of the number of things that it does to make your life as a developer easier, okay? So, like I said, it has limited semantics, which means that there is a whole class of applications which are not going to fit within a MapReduce paradigm. Yes?
So, are you saying that there's not a huge class of applications that don't fit in API?
Fundamentally, no, unless you're talking of NP-complete problems or something which is inherently has a bad complexity. Because it's a fairly low level, you have the full flexibility to achieve it. And you will sort of see some of these examples here where we get stuck. What sort of problems are you thinking that you think is not suited? So unless you're talking of things, so there are cases. So I'll give you simple examples which are, you need to think beyond, you need to separate out between algorithms which are difficult to parallelize as such, even in a theoretical level, and then go to the next step of implementation. So if a parallel algorithm exists, it's fairly straightforward to implement it in MPI. But there are no fundamental limitations to the API which don't allow you to do this. Imagine a simulation of some sort, let's say a heat equation, right? And we have a time evolution of this. Parallelizing in time is hard. So that's going to be a problem with the fundamental aspect of the algorithm that you're dealing with. So I will not hold that against MPI or any other framework because there is a fundamental problem with causality in the base problem that you started off with, which makes it difficult to parallelize. But given something which can be parallelized, and we will sort of take a look at matrix multiplication, which is going to be somewhat more complicated in some sense to do in MapReduce. And you can see it. Actually, for the second assignment, when you implement PageRank, you'll realize that, and for extra credit, all of you can go ahead and try to implement it in MPI because it's going to be like maybe 100 times easier and faster to implement it. And you will see the reasons why it is. MPI being a very basic API that allows all forms of communication or constructs for it. Go back to what we talked about. The fundamental was that you have a send and receive function at a very low level. So any parallel algorithm can be abstracted down to that level, which means that I can handle it at that stage. Whereas in MapReduce, and don't take it against it, it's just the way it is designed, it's much more efficient and easier for a subclass of problems. Like I said, that the standard assumption is that the main part or the main processing that you're doing is something which is very easy to parallelize. It's embarrassingly parallel. It's associated with the data. I'm taking some data, I'm doing a lot of processing on it, and then maybe I'm gathering some extracted results together, which is the most central style of problems that you are trying to solve. Now, if you think of things like Gaussian elimination, something that you will do some variation of this, solving a linear system for PageRank, doing k-means clustering, iterative methods. You don't have a history of things. So if you have to do something repeatedly, it's not that you can't do it. It's inefficient to do it in this. N-body problems, and we'll sort of consider one example of this. N-body problems are like, think of like.
Why is it inefficient? I don't understand.
What do you mean?
Like, no one runs k-means on FPI in the entire way, while Google does it every few minutes.
Yes, actually a lot of people do run k-means clustering on MPI.
Yeah, we're gonna work on the entire web.
They do it actually on even larger problems. The web is not a very large problem.
You mentioned a limitation, right, where data is like continually being updated.
Yes.
This framework doesn't fit. Why is it so hard?
So we take a look at this. The reason is coming from the way it's not, okay, I should take it back. It's not that it's the fundamental limitation is coming from the framework. It's the fact that you have an underlying distributed file system which is not designed for it. And this is less so a problem with MapReduce than with the fact that having distributed file systems which are going to be constantly updating all the files is going to be harder to implement. It's not. And we'll actually look at some options. So there are variations, sort of like HDFS compatible file systems which try to alleviate some of these problems. So we'll go through that later. And the fundamental problem is that you will see when we look at the complexity of doing something like this in MapReduce. And you can try to implement it and you'll realize where the problems are. So yeah, n-body problems is if you have, let's say, a bunch of stars or galaxies, and we are considering the gravitational effect of all of these together. So if there are n stars, computing the effect of, say, the gravitational effect across all of these, it's going to be an n squared problem. And typically, there's a whole class of problems which fall into this category, and they end up being called n-body problems. We're going to see one example, which is not exactly an n-body problem, but it's in the same complexity space, n-graph problems. So these are problems which, and you will see that MapReduce has been used to solve some of these problems by somehow adapting it, making modifications to the underlying framework, but fundamentally it's not very efficient. And when you look at sort of the second iteration of MapReduce, you'll see that there are approaches which somewhat alleviate this problem. And we'll discuss those later in the class. So let's sort of get a little bit deeper into this. Like I said, that we start off with chunks of files from the distributed file system, and they're in sort of these key value pairs. The user code basically corresponds to having a map and a reduce function in the simplest sense. And the first part where there is the map is, given your input files or chunks of files, how do you extract, or what do you define as the key and what do you define as the value? And we'll look at examples, so just bear with me for a minute if you're not familiar with this concept. Once you've taken your files or your data, input data, and converted into these key value pairs, the system, and this is happening sort of transparent to you, you don't really have to do it yourself, these key value pairs get sorted because the way the reduction or the way the merging of this data takes place is using these key values, the keys themselves. So they need to be sorted so that they can be gathered together, and all the values corresponding to a single key are stacked together and passed on to your reducer tasks. And that's where the connection, if at all something exists between your input data, comes forth. So you do some processing, extract your key value pairs, group them together by the key, pass them on to the reduce task, and it works on one key at a time and combines all the value. Again, the manner of combination is dependent. So it seems like a fairly simple framework, and we'll take a look at some examples of how you would actually use this set of two functions to solve some problems. So let's look at word counting here. The input is a set of documents. So the map function in this case would read a document, break it up into a sequence of words, and generate these pairs, where basically the key is going to be the word, and you're just going to have the value is going to be 1. Okay? So that's going to be all your key value pairs. The system, all the map processes are going to generate these key value pairs. The system is going to take all of these, stack them together. So if a word exists, say 10 times, it's going to have the key for the word and 10 ones following that. right? Because that's how many times the value in this case are all the same. So the system groups all of them by key, and given a specific number of R tasks, the number of map and the number of reduced tasks are specified by the user again. They get assigned, and then the reduce basically just simply sums up all values, giving the total count for the word. Now you can do this a little bit more efficiently. So this is somewhat inefficient, because the map in this case, in the strictest sense, is only doing a mapping between the input data and the output data. You can get the map function to do a little bit more work. After all, it's you who's writing the function. So we can actually do a local counting here as well. So you can say that instead of generating duplicate keys, I'm actually going to give a particular word and the number of local instances that you would have for this. And then it's just basically going to reduce the number of key value pairs that your map function generates. And as we'll see later, that is directly proportional to the communication cost. Remember, I told you that it's the input which decides what the complexity of a map reduce task is. Okay? Is this clear?
Sir,
Yes.
is it possible to do like a key and object pair? So I could have multiple value in this.
Yes, so the key value here is sort of open-ended, and we'll see some more examples later. Both the key and the value could be arbitrary. So you get to decide what it is. So in this case, the key is a word, whereas the value is an integer, right? You could have it the other way as well, or any arbitrary data type as being the key, and any arbitrary data type the value. You are exposed to this, right? So you are the one who's deciding what the key and what the value is going to be. So you have the flexibility of doing that.
How do they associate with each other? You like hash table, or
Which ones?
how do they connect with each other? Like
Which ones? The
key and value.
that's just a data structure, right? That's just your thing. You are defining the association.
that depend on how
Yes,
it-
you need a hash when you try to sort your keys and merge them together. So you need to at least have whatever you choose as the key, there has to have at least a membership function for that, so that you can test the equality for them. Because the system will then need to make sure that's how it's going to group them together. And the system is then going to use a hash. Now you can either use the system-wide hash, or you can define your own hash function. The hash is going to be used to take these keys to figure out how it's going to get assigned to the reduced tasks. Now, if you have a specialized application where you think that the standard hash is not going to do as good a job, you can go in and plug in your own hash function, which is going to determine how you're going to map from the keys onto the reduced tasks. Okay? Those are specifics which we'll get to maybe later, but fundamentally this is the. How would you do this if you were doing it in MPI?
Each processor will kind of calculate the subgroups.
Mm-hmm. Of?
Do sum them up in each node,
Mm-hmm.
and then do some kind of what do you call it? You do a progressive sum, so that you can add each word at a particular spot. So that
What do you mean by progressive sum?
cumulative sum of the dictionary values, so that they can speed up the
Distribute the set of documents to different nodes
Yes.
with the number of processes, count the words in the document, collect the words in one parent node and add it to others.
So the one issue that you're going to have is that you're going to have to take your words, or the keys in this case, and distribute them across the processor, because only then can you do it. Or make sure, depending on how many words there are, you might have to have the words on every single process, right? Because you can do a reduction. I want you to think about reduction as is defined in the MPI sense versus reduction when we talk about here. And it's sort of important to make this distinction. When you start off, I know that you all went through this MPI thing, so when you talk of reduction, you talk of all the tasks, half of them happening in a binary fashion, because that's the least complexity out there. Reduction here is a little bit different. Reduction is taking a bunch of inputs onto a single node and doing the sum there. That's it. There is only one layer there, right? So you have fundamentally, the parallelism needs to be broken down at the first level. At the map level itself, I have broken it down to saying that these are the words and the indices that I've read. All the words with their counts are going to end up on a single reduced node. So that's the end of your parallelism at that point. And this is important to realize.
If map reduce, that's the end.
That's the end. Now you can have, we look at some cases, but what I'm saying is that if the duplication within, for a number of words, was larger than the, let's say how much I can receive, and we look at the complexity of this, at a single node, I'm done. Whereas in the reduction, in an MPI sense, is not limited by what is the capacity of a single node. Is that clear? There is very limited parallelism, which is fine for these many of these applications, but you need to understand reduction here is a bunch of inputs ending up in a single reduced node as opposed to still being distributed. So when you get to the reduced stage, you've sort of, that's the end of parallelism to some extent. Yes?
You were saying like this thing, reduction and map reduce. In MPI we can do it in a binary level, like
Yes.
2 to 1 and then like. Why can't we do that in map reduce also? We can do that, right?
You can. So you can stack them together. The problem here is the overhead of creating these tasks, whether it's a map task and a reduced task, is so high. And that's the thing. It's not that you cannot do it. So you can create a bunch of, so let's say you do the first level reduction, and then we say that all of these, when we look at the matrix multiplication, you'll think of a 2-pass algorithm, where you have a map, a reduce, followed by another map and a reduce. In reality, the second map is just an identity. But in terms of the framework, we are going back to disk every time. We are spawning new processes. We are scheduling and synchronizing everything. So if you cannot, in some cases you might not have an option, but if you cannot then, do it in a single pass, you're paying a huge overhead for a second iteration, whereas in MPI, the overhead of doing something in a recursive fashion or in an iterative fashion was almost zero. Compared to this, yes.
So you said that in the reduced level you're supposed to have one single reduced node.
Yes.
Is it always the case? Because
It's not that you're having a single reduced node. I'll partly answer this, but wait on a minute if it's not clear, because we get clear when we look at the complexity. What you're saying is that I've broken down my input in a sense of the things which need to be reduced together. In this case, all occurrences of a particular word. It's not all the words, but the reduction needs to be performed for the number of the local counts for a given word, right? That's where I needed to combine inputs from different sources. All of those need to end up on a single node or a single reducer task.
yeah, I mean each word needs to end up on a single reduced node.
Yes.
But it doesn't. So if we have n words and
Yes.
r reduced nodes,
Yes.
we can have n by r.
Yeah.
words in
So
each.
you can have multiple words ending up on the same reduced node
Yes.
or a reduced task, but the opposite is not true. What I'm saying is that you're still limited by how much data, for whatever reasons, whether it's a memory issue or maybe it's a I/O issue or a communication issue, that is your bottleneck, and that is fundamentally exposed even at the map level, because that's where we're deciding how much data ends up on a given reducer. And it's particularly hard, although a lot of all the other examples we are going to consider are going to be somewhat symmetric, especially if you think in terms of a matrix multiplication. In this case, you might not know a priori what the distribution of these cases is. So I don't know how many. So my different reducers, if you think of having one reducer for every single word, the amount of work, the amount of reduction that a given reducer has to do is going to differ across the different reducers, which becomes a challenge in its own because it's not straightforward. And given that this is actually typical of a lot of the standard problems where MapReduce gets used, the way you set up your system in terms of having, let me see, maybe it's the next slide. Yeah, let's look at this. So you need to think in terms of where the parallelism is exposed, right? Try to distinguish between each of these. When I talk about reducers, I'm talking about the single mode. This is at a fundamental level, not at an implementation level, the level of the smallest reduction that you're going to do. In this case, summing up all the counts for a single word. That is a reducer. So the total number of words that I have, all the words in all the text, that's the number of reducers that I have. That's the level of parallelism that I cannot subdivide further, right? So that is the number of reducers. We are also going to talk about reduce tasks. These are the processes which we have running that are going to take these. So you might have multiple reducers assigned to a specific tasks. You might also, depending on the complexity of each of these, have multiple tasks running on a given compute node. So if you have a node with multiple cores, you might say that I'm going to run 5 reduce tasks on these. And skew is this imbalance that you might get because your input data is different. And I cannot predict this, which means that I need to now schedule these, my reduce tasks and my reducers across my available resources, trying to balance it. And Hadoop tries to do this in a dynamic fashion. Whereas when we do this in something like MPI, we try to do it in a static fashion, more at sort of coding time, or you try to make decisions on how to do this, right? Or you come up with the right strategy depending on what you would expect. This is the reason why Hadoop gets, when I said that it's more complicated to implement Hadoop itself or MapReduce, is because of this reason, because these kind of decisions are happening behind your back. As long as you've chosen the right factors for these, you have the parameters to the system of, what is the number of reduced tasks that you want and how many nodes do you want to run it on, the system is going to try to do its best to schedule these tasks in a dynamic fashion so that they get your resources get utilized properly. That makes it easy to implement. At the same time, if you're not careful, it can be very hard to get performance. So that's the trade-off that you have to think of. Yeah.
What is the significance of sorting here in word count problem, especially?
It's not, the sorting is not happening from a word count perspective. This is happening for all tasks, or all MapReduce jobs. Once you get the keys, right? So this is where you're gathering information together. This is the fundamental framework that MapReduce uses to say that I can gather. If you generate a bunch of words, let's say one of the words is reduce, right? And another map process, he also generates some, the count for whatever the number of times reduce occurs there. I need to make sure that these two end up on the same reduce task, because the framework doesn't allow parallelism across that. So I need to put them together.
Why you need to sort them? See, if I generate a reduce word,
yes,
I build a hash function so that it will give an output of reducer number.
Yes.
So every key will go to that particular hash function and get the number of reducer. So even if I generate a reducer, you or someone, that will end up in the same reducer number. That's one.
It depends on what is the quality of your hash function. So invariably when you...
Considerably it is the best hash function available.
Sure, in this case you can directly map it, yes.
Okay. So there is no sorting here.
In that case.
Okay.
But fundamentally, for the more complicated cases, you would sort them because there is an inherent assumption that you make that there is, even if you use a hash function, you might want to do some sort of a locality sensitive hashing, in which case I might want that key number 5 is close to key number 6. So you might have, the sorting is done so that you can actually arrange it. This is what happens at a more implementation level. And so in case I am designing some of my algorithm, let's say we're talking of matrix multiplication, where my keys might actually be the rows and columns, right? In which case I want them to be close by so that I can map them. In which case, again, you want to sort them because that is there. Now, this is sort of when you think of a generic framework, you have to support these kind of things. And that's why you sort of end up sorting the keys, because these are the only flexibilities you have is to define your map and your reduce function, which means that you fundamentally would rely on the way the keys get mapped onto this. You can override your hash function as well, which could again be required for more complicated MapReduce tasks. Okay? We'll look at some of these examples where it is important the way the keys get assigned, because you are the one who's choosing these keys. Clear? Now, I talked about why fault tolerance was very important, and this is sort of the fundamental reason. We're not going to go very deep into this, but try to understand how a MapReduce system would recover from a node failure. Most of this is for sort of the early implementations that people have come up with solutions to address some of these issues, especially the first one. If the master node, so there is a master node which is coordinating everything in MapReduce. If the master node fails for whatever reason, then we have no choice but to restart it. In Hadoop version 2 and some of these other things which have come up as a result of trying to fix these problems, you have a duplicate or set of duplicate head nodes which can actually take over in case the master fails. If the map worker dies, this is a particular node which is running a map task, then there's a couple of things that need to be done. The most important thing is that all the tasks that are assigned to this particular worker need to be redone. This is because of the fundamental requirement that you had a distributed file system, which means that there is no guarantee that the tasks that that particular worker might have finished are actually synchronized across the file system, which means you cannot rely on that, so you have to redo this task. So basically the master is going to set this guy as idle so that no work gets assigned to it. And he needs to also inform the reduce task on where the inputs are going to come from, because you've reassigned these tasks. If a reduce worker does, it's actually much easier because you would just simply mark that particular worker as idle. So that particular chunk of work, which reduction that had to be done, will just simply get assigned to the next available free reduce worker. This is stuff that you don't have to deal with. This is what the system sort of provides you to deal with this. So now let's move on to cases that we are sort of more comfortable with. Matrix vector multiplication, right? So this is, think of it almost as one step of your matrix multiplication. So we have an n by n matrix with entries mij, and we are given a vector of the same length, n, with values vj, and we need to compute this application of this vector multiplied with the matrix, right? So this is a standard expression. The solution is here, but I want you to think about how you would take something like this and map it onto MapReduce. So again, the goal for the map process is to generate a key and a value, and the reduce is to gather them together. In this case, we're going to generate I, where I is basically the index. So look at the input and look at the output. If we can fit this whole V into memory, right, if it is large enough, every single process is going to load the entire vector. Every single map process is going to load V into memory, and it's going to load the corresponding
Parts of
matrix, the corresponding row or the column, depending on how you want to define it, whether you do a row major or a column major format. And then it's going to compute the product of those two and set it up to the I and leave it, right? And that's your key and the value. These will get mapped on by the system and sent to the reducer. Any given reduce task is going to be assigned to produce the entry xi. And it's going to sum up over all of those to give you a key I and the value, right? What do you do if, yes?
What if one row is so big that it can't fit in?
So that's the next line here. So the strategies are going to be very similar to what you would do in a MPI case, and actually is the most default case. So if this is my matrix, right, and this is my vector, and if the vector is if n is too large basically, then you're going to partition this across different processors. So each process is now going to load only a subset. Correspondingly, we are going to divide our matrix M into blocks as well. So let's call these groups, and we will see this being used quite extensively. So now the key is going to be a little bit more complicated because you're going to have I out here, this entry, but now you're going to have also a group, let's say 1, 2, 3 out here. So the reduction will have to take care of each of those and gather them together. So each of these guys, right? Yes.
So in some case we're generating two keys and saying the two keys are the same key, or
No. It's the key is still going to be I, because this is still I. It's just that now you have more parts. So there are going to be additional keys being generated because each of those is only subparts in memory, right? Right? And that's all.
Where does the distributed file system come into picture?
So when you deal with this, it's not. The distributed file system is in the underlying framework. So this, as far as you are concerned, you don't see it. Because the input file, so the distributed file system is going to be in the sense of where is M and where is V. M and V are going to exist as files on the distributed file system. Because of fault tolerance, Hadoop is actually going to break these into smaller chunks and actually duplicate them across, typically in 3 separate copies, one on a given node, one on and other two on 2 separate racks, so that even if the rack goes down, somebody else has the file. When you write your map function, you want to access M, the map tasks are, in an ideal sense, going to be assigned to nodes which would have the information that you need local to that file system. And that's what the system does for you. This happens as far as you're concerned. In many cases, you can go down deeper to mess around with it if you have specific needs. But in most cases, that's why it's easy to implement, because you don't have to deal with this. It happens transparently to you. You don't have to deal with the DFS directly. Okay?
So in this example, one of your vector part of the map task would be to bring all of this vector into on one node.
Yes. So you have to deal with that. So we are sort of skipping some details here because we are also assuming that the map task that you write can easily, in a completely efficient fashion, access Mij and Vj, right? Whereas depending on how the files are actually stored, it might not be that straightforward, because especially the matrix is a 2-dimensional structure. So I might not. We are sort of ignoring how exactly you would read it in an efficient fashion so that everybody can access this data. Okay, but at least for the time being, let's assume that you've chosen a reasonable files format so that we can, any given map task can directly say that I need Mij, which is basically the entry at the ith column and the jth row, and access that from the file. Okay, that we sort of are ignoring right now. That is going to be somewhat implementation dependent as well.
So like different vendors can have like different.
Most Hadoop things will, because it's standardized, will be there, but I'm pretty sure Google's implementation is going to be, for example, different. And Phoenix is probably going to be somewhat different as well, as you access this. Because this is very closely tied up with the distributed file system. That's why when you typically look at MapReduce, you are sort of connected with that, because the system has to provide access to this and to schedule the map task and correspondingly at some point the reduce task, so that it is local to the disk. Because if you arbitrarily schedule your tasks, then you are always accessing data from some other portion of the DFS, right? So you want this mapping, the map where it gets assigned, to be mapped directly onto the, close to the data as possible. Right?
In the second two-phase algorithm.
Yes.
The first reducer, if you convert into mapper, then it will be into one.
Which one? Which map?
Reduce one.
This?
Yeah.
What do you want to do this?
If I convert that into
Yeah,
mapper,
to some extent, yes, you're right. But what is the price you pay? What is the downside? Why don't you want to do this? This is the one-step process. Why? So what I'm doing is that for a given ij, for a single entry in the matrix, right, I'm producing n keys. I'm creating duplicate keys now. So this is mij, j is fixed, right? But I'm producing ik, as in I'm producing duplicates for every single k. Understand? So I'm producing n keys and n keys for every single input that I had.
That
So
will be JK, right? Second JK.
which one? Yeah, this is JK. Sorry, this is JK. In this, yeah, that's JK.
So for k is equal to 1 and k is equal to 2.
No, sorry, no. This is correct. This is correct. Sorry, this is correct. So in this case, I is coming from the data, and I'm producing k equal to 1 to n duplicate keys for this data. Here, k is coming from here, and I'm producing I equal to 1 to n duplicates for this key, right? Is it clear? Sorry, I got confused, but yeah. You understand what I'm doing? So think in terms of input. What is the input? The input is mij or nij, njk, right? These are my input values. For each of those, I'm producing redundant keys because that's the way I can do this in one step. Okay? So once we have this, we can have the reduce guy, which is going to gather everybody with ik, right? Which is going to be how many entries?
N square. I'm into N. I'm into N.
Why?
First.
Each value is already multiplied n times, right? I duplicate it here, right?
Yeah, so in this case, we are going to get, yeah, 2n square.
2n square, yeah.
2n square. N square from here and n square from here, and that's the amount of data that I'm going to get together. Then I'm going to sort it by j internally. Let's ignore how you do this at your reduce. You're going to extract these, multiply, and accumulate the sum.
Why do you have to sum it?
Sorry? So that you can multiply, and if they sort it by j, then I'll get mij and njk together.
Oh, okay.
Because then only I can, you know which ones to multiply by which, right? There are n square terms on each side. I need to make sure that they both come together.
Okay, yeah.
Because that's what you need to do, right? You need to do mij times jk, right? Is this clear? Is this a good algorithm, or is the previous one better?
Depends on how you do it.
So what we're going to do now is to look at how do you actually analyze the complexity of something like this, because there is a trade-off. The trade-off is that the two-pass algorithm, so this definitely looks like has more communication, right? Is it worth it? Because there is an overhead, like I said, of creating a second MapReduce task. So you're launching new processes, you're writing things to disk and loading it back again. So you need to understand how these two relate. And so we're going to look at the complexity theory for MapReduce. How are we going to do about this? I sort of mentioned this already. This is just a quick summary again, that we're going to say that the communication of a task is related to the size of the input because the output is probably less. We're not going to consider the execution time for doing whatever you're doing, whether at a map stage or at the reduce stage. And then the output is significant, usually much smaller, so we can ignore the size of the output as well. Also think in terms of that the output of the map goes as an input to the reduce, so you can ignore it to some extent there as well. So these are important concepts that you should think about when we start to analyze a MapReduce. the first we should think about is the reducer size, which we're going to represent by Q. Now the reducer size is the upper bound of the number of values, key value pairs basically, that are allowed to appear at any given reducer. Okay? So we sort of did this analysis just now, which is any given reducer. So in the word count, this will be the number of words that actually exist, and in that case it's not symmetric. In the case that we just considered, it was 2n squared because we got n squared from m and n squared from n showing up at a single reducer. Okay? So this, and we'll go through these examples, we'll work these out, is going to tell you, is an indicator of the upper bound on how much we can, how much input we receive at a reducer. Why is it important, and why should you think about it? Because if you make the reducer very small, right? If it's really small, then we can force there to be a lot of reducers, which means that if the reducer size is small, then the number of reducers is very large, corresponding to the input, which means that we have a high level of parallelism, right? So that's one way to look at it. So there is a motivation to reduce the reducer size. There is also another reason to reduce it, which is that keep in mind that most of these tasks are going back and forth from file. So if the reducer size is small, then it's possible that we can have all of this stored in main memory, in which case you're going to still be efficient because you are minimizing I/O. I told you communication and I/O, these are the two things that we are trying to effectively minimize, right? The other factor that you should think about is the replication rate. This is directly related to the communication between the map and the reduced tasks. The replication rate is the number of pairs produced by all the map tasks divided by the total number of inputs. In the matrix multiplication case, it's completely symmetric, so it's the same, but in general, this is an estimate of the average communication from the map to the reduced tasks. Is this clear? Do you understand these two numbers?
Can you go with the second?
So this is just telling you, you look at all the key value pairs produced. So you had some input, and the map is producing a bunch of key value pairs. For example, the one-pass algorithm produced way many more key value pairs than the two-pass one, right? We take all of them and divide it by the number of inputs. The number of inputs is going to be the same. In the matrix multiplication case, it's 2n squared. We have 2n by n matrices, so the input size is 2n squared. Now you have different algorithms for doing this using MapReduce. Two we considered just now. So the question is, can we actually now go ahead and get an estimate of what is the average? So this average tells me from a given map task, what is the average communication between a map and a reduced task, right? Clear? So we're going to use these two to characterize our algorithms to get an estimate of how exactly they are, because that's what's going to tell us which one is better in which cases. So let's just quickly go through this. This is very easy. Matrices are n by n. R is the replication rate, right? Each element produces n keys, right? Each Mij, I produce that many duplicates. Similarly, Njk produces n keys, right? Correct? Each input produces exactly n keys, which is good from a load balance perspective. What is the reducer size? Each key has n value from m and n values from n. So the reducer size is 2n in this case.
What's the replication rate?
The replication rate is the total number of keys produced divided by the total input, right? Or the average number of keys produced per entry. That is our replication. Consider the two pass, it will become a little bit clear. The replication, each element produces only one key, right? It's just going by itself. Again for this, so each produces one key. In the second pass, again it's producing one key because you've already multiplied them together and you're now gathering them together. The reducer size, so each key has n values from n, and it's the same case as the other case, but there are two passes. In the first case, you're getting from both. In the second case, you're only summing up them. So It's 2n in the first pass and n in the second pass. Right? Just counting these numbers out here. Let's look at a real world example for why these numbers would make sense, right? Let's say that we have a real world problem to solve. This is the problem. We have a large set of elements and we are given a similarity measure. Let's say that these are images, okay? So think in terms of there is a database of 1 million images, right? Each of them is 1 megabyte in size. Seems reasonable? That's not a very bad problem, is it? So 1 million images, maybe some of you have your own image collections which are this big. So the goal is that we want to find pairs of images which are similar. So you have a bunch of images and you want to take all of them and say that let's figure out all the images which are together, all the cars, all the people, everything we group. And again, we're not going into the specifics of it, but let's assume that there is some similarity. Given image X and image Y, it can compute a similarity. Maybe it's just a difference between the two. Maybe it's looking at the color histograms or something. And if it is, so the input is going to be some ID and the image, right? And output is PI, PJ, or simply the indices for those pairs where the similarity between PI and PJ is greater than some threshold. Is this clear? Does this seem like a very big data problem? Why?
Because each image has to be compared with every other image.
Yeah, but 1 million images, 1 MB, isn't that bad? It is an n square. This is why I said that this is sort of your n-body type problem because you're again having an n square, which is there. But in terms of data, is this too bad? What is going to be the challenge here? Is the computation going to be the challenge or the communication? Yeah, let's ignore the measure. Let's say that you have a black box, you give it 2 images and boom, you get a number.
But sending the images through the
Right.
File size is very small. File size is very small compared to
Yes. So let's try to improve that. Okay, so let's look at how we would analyze something like this, right? So let's go for the simplest MapReduce. And one of the goals of giving this example is that I don't want you guys to go ahead and implement the first thing that comes to your mind when you do. And that's one of the downsides of MapReduce, that most people might end up implementing something like this. So the map function is easy. Let's generate a key value pair. I'm just going to take the key as being ij for every possible pair, and the value is going to be pi pj. It's clear? This is not too bad, right? And what is wrong with this? Yeah. So reduce is also reasonably simple. Apply the similarity function to each value, right? And output pair if similarity above the threshold, right? This is embarrassingly easy to parallelize. But now let's look at the matrix we talked about. What is the reducer size? It's 2, right? In terms of memory, that's 2 MB because the value is going to be 2 images. This is a very small reducer size, which means that the level of parallelism is very high, right?
Sorry, reducer size is it above the threshold or below the threshold? Is it patch or two keys?
What is the input? How many keys do you get at every given reducer?
Oh, okay.
I have one reducer assigned to each key. There's only one guy to each key,
Okay.
right? So each reducer just gets one key, one value,
Okay.
right? Yes?
Yeah.
What is the replication rate? This is basically n, right? N minus 1. You're not sending it to yourself, but it's for every pi, I'm generating all pj combinations, right? So every input gets replicated that time. This is the total number of keys generated, which is n squared divided by the total number of inputs, which is n, right? Or n square n minus 1 by n, right? That's what it is. So this is almost 1 million. So what is the total communication from the map to the reduced tasks? We have 1 million inputs, correct? times the replication rate, I'm ignoring the -1, times 1 megabyte. Again, I'm approximating by 10 to the power 6. That's 10 to the power 18 bytes. That's 1 exabyte. For those of you who want to know where exabyte is, it's giga, tera, peta, and exabyte. So for something which doesn't look like a very big problem, we are now ending up with 1 exabyte of communication. This is a contrived example, but assuming that all of this had to happen over a gigi connection, we're going to take 300 years just to exchange this data from the map to the reduced tasks, right? So this is not going to work. Did you guys think this is going to be this bad? So how should we do this? This is a hard problem to solve. I'm not saying that this is the kind of problems that you're going to be solving. But what would be one way to do it? And we sort of considered this when we were doing the matrix vector multiplication at least. What would you do?
Aggregate the files.
How? So again, these numbers tell us what it is, right? So if we look at the total communication, right? So one option is that reducer size, right? The reducer is not doing enough work. It's only getting 2 values at a time. It has enough memory as well. It's only using 2 megabytes, right? Your average machine, average compute node is going to have way more memory than that. So you want to do more work here, correct? So
compare any images that way.
no, what you would do is to group images, okay? So let's sort of generalize this a little bit. Let's group the images into G groups, such that each has 1,000,000 by G images each, okay? So then, what we are doing is that we take an input element IPI, the same as what we had there, and instead of generating n keys, we say that we're going to generate only G minus 1 keys. So we're only exchanging it with groups, with other group. Okay? Is that clear? So basically you're doing G minus 1 keys, where the key is now U, comma V, which is the group IDs. So these are no longer going from 1 to n. So instead of n square, we have G square, order G square keys, such that picture belongs to the group U, and V is going from 1 to G except for U itself. In an MPI sense, you can even think, let's ignore this also. Even though I've written it there, let's say it's just going G groups instead of G minus 1, right? So the associated value, that's the key, U comma V, and the associated value is going to be IPI. You still need I because you need to know which of these indices this picture came from. Consider the reduce operation now. We're going to reduce based on the UV keys, which are going to tell us which pair of groups we are dealing with here. Associated list will have 2 times 10 to the power 6 by G elements, right? So each group has 10 to the power 6 by G, and we're getting a pair of groups, correct? Like this. We'll take each IPI and JPJ in this list, where they belong to different groups, and compute the similarity and do the thresholding and everything exactly the same way. But now, instead of having a reducer size of 2, it's 2 10 to the power 6 by G, right? You have still one other issue, which is how do you compare pictures belonging to the same group, because here we are comparing only when they are, because you'll have multiple groups. One option is that you skip this guy and say that I'm going to have groups of the sort U, comma U, or you can use a heuristic which saying that the reducer which is designed for U plus 1 or U minus 1 will also process the self-similarity. Is it clear? So this doesn't seem like it's a very difficult concept, right? All we have said is that instead of dealing with all of them independently, we're going to group them together so that we increase the work that a given reducer does. And what is that? I'm running out of time, but very quickly, replication rate is now down to G minus 1. The reducer size has gone up from being smaller to larger. And in general, you're going to notice this for a lot of the cases that R and Q are going to be inversely proportional to each other. And the trade-off between different algorithms is going to be to balance these out so that you get the right performance. Input size has now 2 times 10 to the power 12 by G bytes. Say if we choose G is equal to 1000, which is that there are 1000 images in each group, then the input is going to be 2 GB per reducer, and the total communication has dropped to 1 petabyte, which is still a lot, but at least we've been able to scale it down. Okay, so